Hi, and welcome to Office Hours with Professor Eric Bogatin. That's me. This is for on November 17th, 2025. For a lot more information about this episode and all the details, check out my Substack page. Here is the QR code. You can access the website directly either from the URL over here or by scanning the QR code. In this episode, this is really a three-parter. We're going to be looking at a really useful and easy to use tool from Sierra Circuits that can be used to analyze a few important signal integrity problems. In particular, in this series of videos, we're going to look at using their transmission line impedance analyzer, the reflection bounce diagram illustrator, and the maximum current and trace resistance analyzer. And again, a lot more of the details can be found in my Substack newsletter, so I invite you to go visit that and you can sign up for it and view all the content for free. So let's get started, and in this particular video I'd like to review the transmission line impedance analyzer. To get there, all we have to do is go to the Sierra Circuits website, and right at the top here we see designer tools. We click on that, that takes us to all the designer tools. The first one that we're going to look at is this one that says impedance calculator. Its sole purpose is to take stack up information and turn it into some of the electrical behaviors, characteristic impedance, capacitance per length, inductance per length, time delay, that sort of thing. To access it, we're going to click try this new tool, and you can review some of the details here, but I'm going to walk you through a couple of examples. And so there are predefined cross-sections of different transmission line structures. We're going to use these structures, first identify which one is close to the structure that we're interested in, and then we're going to input the input information, and the output is going to be the transmission line properties, the characteristic impedance and time delay. Behind the scenes is a 2D field solver, and so the absolute accuracy is something in the order of about 1%. There are a couple of different types of transmission line structures that have predefined. Over here in the bottom part, we can select what kind of transmission line: single-ended, differential, coplanar. You see the different geometries that are available here. We're going to do something really simple and just do single-ended initially, and then you can peruse this and evaluate at your leisure. And then given the type of cross-section, then we can have different features. We're going to look at the case of the uncoated microstrip. Coated just means there's a solder mask on top, there's embedded, and there's strip line as well. So these are the variety of predefined structures that are involved. Now when you open up and look at the different structures, you'll see some of them say open, the others have a little lock here. The ones that say open are available for anybody. You don't have to register, you just click on those to use them. The one that have a little lock here, they require you to sign up and register on their website. It's still completely free, but you have to go through the registration process in order to unlock a lot of these other structures. So we're just going to take a look at a simple uncoated microstrip. We're going to open that up. We're going to get this form that's set up. Here is the cross-section information of the microstrip. You can see each of the features are labeled in the diagram. It's really easy to follow. And we're going to input some information. There are two ways of using the tool. The first is pure analysis. This is the structure we've got, and we want to go ahead and analyze what's the characteristic impedance. And so we're going to fill in all these variables, and then we're going to come over here and say, okay, now that we're done, here's the design of the structure. What's the characteristic impedance? The second way of using it is, generally, we're going to know what the dielectric thickness is. We're going to know what the dielectric constant is. We're going to know what the trace thickness is, for example. We may not know the line width for the impedance that we want. And so we would fill in the information that we know, except for the line width over here, and then we would type in the target impedance that we want, 75 ohms in some cases, 50 ohms in other cases. And once we have that target impedance, then we would click this button that says calculate the line width, and it would tell us, okay, given the rest of the parameters, here is what the line width needs to be to give you that impedance. So I'm going to walk you through two examples just really quickly. It's the kind of thing you want to come back and play with at your leisure. But I'll show you how we use it and how we can gain useful insight in learning about transmission line behavior with this tool. So we're going to start out just really simple 2-layer board. Typically it's about 60 mils thick. Dielectric constant, depending on where you get it, is 4.8. How do you know what it is? That's always a tough question. You always start with the nominal value you get from the fab vendor. So websites like PCBWay, JLC, a lot of other fab vendors will tell you what the dielectric constant is for a particular stack-up design. That's the nominal value. Different issue about how accurate it is. All we can do is start with the nominal value unless we have better information. So we'll start with 4.8, and then we'll start with the line width. I think around 100 mils is going to be roughly 50 ohms. We can also explore the etch back. So this is the difference between the bottom width and the top width. For now, we're going to make that 0. So we assume vertical rectangular walls. And then for trace thickness, this is in mils. We're going to use 1 ounce copper, so that's 1.4 mils. So we have all the input information here that we know. We're ready to calculate, and we want to know what's the characteristic impedance. We come over and say calculate characteristic impedance, and here we go, 51.8 ohms. Okay, now comes the synthesis part. If we wanted to hit a 50 ohm characteristic impedance, given these other dimensions, this is uncoded, so no solder mask on top, we could say, you know what, I really want a 50 ohm line. Tell me what line width to use. And we say calculate the line width, and here we go with 105.7, basically 106 mils as the line width is what we would need for a 50 ohm line. While we're here, and we've just done this calculation and we've got a impedance of 50.2 ohms basically, we can ask the question, well, okay, if we make a small change, suppose that we had some etch back. Suppose the top of the trace was narrower by a half a mil on either side, so that's 1 mil. So our etch back was 1 mil. What would be the impact on the characteristic impedance? So given this line width for the as measured at the bottom of the trace, the as designed line width, if the top is over etched a little bit and it's a 1 mil difference between the top and the bottom, what will that give us for the characteristic impedance? Now remember that if it's rectangular, it's 50.2 ohms. And remember, before we do a measurement simulation, we always want to apply rule number 9, which is never do the measurement simulation without first anticipating the result. So let's think of this. We're taking a line with square walls at 50.2 ohms, and now we're bringing the walls in a little bit, and so that means that we're going to have a tiny little bit fewer field lines going from the top to the bottom here because they're a little bit farther away. Fewer field lines, lower capacitance, a little bit higher impedance. So we would expect a little bit higher impedance by having that etch back compared to the rectangular walls of 50.19 ohms. Let's see what the new characteristic impedance is. And sure enough, it's a little bit higher. Not a lot. 50.26 ohms is the higher impedance. And so we can evaluate these kind of second, or sometimes in this case, third order effects using the built-in 2D field solver. So this is a great, useful tool. It's really simple to use. It's basically free to use. I think it is a far better tool to use than a lot of the online calculators, because all the online calculators that are available are basically approximations under the hood, whereas under the hood for the Sierra Circuits impedance calculator is really a 2D field solver. So be sure to check it out, and check out my Substack column for this week, November 17th, 2025. Thanks for joining me. Welcome to this episode of Office Hours with Professor Eric Bogatin. This is from November 17th, 2025, and this is actually part 2 of our series. We're exploring what I think are 3 very useful and easy to use tools for signal integrity analysis that are available on the Sierra Circuits website. Here's the link to their website, and we looked in the previous video at the transmission line impedance analyzer. In this video, we're going to take a look at the reflection bounce diagram illustrator. All the details about how to use these tools and the valuable information they contain and what we can do with that information and the principles behind them are reviewed in my Substack episode for November 17, 2025. You can either go to the URL for my Substack website, or you can scan the QR code here, and that will take you to my Substack site as well. You can view this episode, the previous ones, and you can also sign up to join the newsletter and receive your own copy of my columns periodically as they come out. This particular online tool I think is a really useful tool to help understand and exercise our understanding of how signals interact with transmission lines. So let's open it up, and I'm going to walk you through really briefly how to use it, what you can get from it, and how you can use it to increase your understanding. And in the Substack column for November 17, 2025, I offer a couple of exercises for you to go through to help you exercise your understanding. So let's take a look at the website. So here's the Sierra Circuits website. We come over to the top here under Designer's Tools, and the one that we're going to look at in this particular video is the one that is the Transmission Line Reflection Calculator. So we come over here, we say, okay, try this tool. It's completely free, don't have to register for it. And here's basically what it's going to do. We're going to build a very simple transmission line that has a source with a Thevenin model. That means there's a source voltage and there is a Thevenin resistance, output resistance. And that source is going to be a step edge. It's going to turn on, stay on, and we're going to look at the voltage at the other end of the transmission line. So we got the Thevenin source, we got a uniform transmission line, and we have a load impedance at the end of the transmission line. And we're going to look at the voltage at the end of the transmission line where the load is, and at the source of the transmission line right after the Thevenin resistance. In particular, we're going to pay attention to the voltage at the end of the transmission line. And if we really understand how signals get launched into transmission lines, propagate, reflect, and what we would measure as the total voltage at the end of the transmission line, then we should understand and be able to predict exactly what we're going to see in this tool. And that's where the useful learning exercise comes in. If you can really predict what we expect to see at the end, we run the simulation, we see that, then that's going to give you confidence that you understand transmission lines. If you can't predict it, you want to go back and study a little bit more about transmission lines. And in my Substack episode for this week, the 17th of November, I have links to a number of free resources for you to learn about transmission lines and how signals interact with transmission lines. So let's get started, and we're going to come up with a couple of really simple examples initially. In the first case, we're going to use a source impedance that is 50 ohms. So it's matched to the line. We're going to use a line impedance of 50 ohms. So the source is 50 ohms, transmission line is 50 ohms. Now, it doesn't really matter what voltage we say is launched in or the propagation time, because everything is going to be auto-scaled on it. But just to have a number in there, we're going to have a 1 volt as the launch signal, easy to estimate in our head, and we're going to use 1 nanosecond as the propagation time. And now we're going to adjust the load impedance. In this particular case, we're going to make it 1 meg, so it's a really high load impedance. Now we're going to anticipate, we're going to apply rule number 9. We're going to anticipate what we expect to see. So, got a 1 volt source, 50 ohm series transmission, 50 ohm series resistor, transmission line that's 50 ohms. When we look into that transmission line initially, we're going to see 50 ohms. We built a voltage divider, and so 1 volt comes out of the source, but it sees that voltage divider. Half a volt gets transmitted into the transmission line. That's what we're going to see as the voltage launched into the transmission line. That half a volt signal propagates down to the end of the transmission line, and at the end of the transmission line it sees an open. What's it going to do? Well, reflection coefficient from an open is 1, so half a volt goes in, half a volt reflects. The voltage we see at the end is going to be a half a volt plus a half is 1 volt. That's what we expect to see. Initially, we're going to see at the launch, the initial voltage is a half a volt, propagates down, we see 1 volt to the end. That half a volt reflected signal heads back, and after a round trip time, we're going to see it as 1 volt total voltage at the input. So remember, keep separate the signal that propagates and the voltage that the scope is going to measure, which is the signal is effectively a vector. It has voltage and magnitude and direction, propagating in either left to right or right to left directions, but the voltage that we measure on the nodes at the far end or at the source, that voltage, what the scope would measure, is a scalar, has no information about direction. So let's see if we simulate what we expect. We should see 1 volt initially, and then we'll see half a volt initially at the beginning of the line. That'll then rise up to 1 volt, and after the signal hits the source, it goes 50 ohms in the transmission line to 50 ohms at the source. No more reflections. Let's see if that's what we get. So here we go. We calculate it. And it turns on, and so we see 1 nanosecond later. What do we see? Oh my gosh, 1 volt, exactly as we expect. It turns on at the source. It turns on. We get the half a volt. It goes down and back a round trip time later. We see the half a volt coming back to us. We see the 1 volt at the source. Exactly what we expect to see. If you understand this behavior, you're most of the way there understanding the behavior of a transmission line. There are a couple of other special cases that you can look at. Of course, the interesting one is, if the source impedance is really small, like 5 ohms, let's make the end of the line terminated. We'll make that at 50 ohms. Now, what do we expect to see? Well, let's see. If the source is 5 ohms, we see 50 ohms looking in. We have a voltage divider. We're going to see 50 over 55. That's like 1/11, so that's about 0.9. So if 1 volt comes out of the source, 0.9 of it is going to get launched into the transmission line. We're going to see that at the far end, a nanosecond after it turns on. We're going to see 0.9 volts, and it's going to see the 50 ohm. It's not going to reflect. We're going to just, the signal's going to turn into heat, and we're going to see 0.9 volts forever as long as we look. Let's see if that's what we get. So we're going to calculate it, and let's see. And sure enough, look at that. 1 nanosecond later, there's our 0.9 volts that we see, and it'll last there forever. We'll do one last example, and these are the kind of examples that you should do to exercise your understanding. Go back to my Substack column for November 17, 2025, and I list a couple of other examples that you should look at. But let's do just one other example. We'll keep the small output impedance of the source, but we'll make the line open. So we'll put 1e to the 6 at the load impedance. Now what's going to happen? Well, most of that voltage, 0.9 volt, gets into the line, hits the end, reflects. We're going to get like 1.8 volts at the end of the line. That 0.9 volts heads back. It's going to see the low impedance. It's going to reflect, change sign. It's going to come back. We're going to see a negative voltage. That voltage is going to drop. It's going to reflect. It's going to go back, change sign, come back, and we're going to see ringing at the load. Let's take a look and see if that's in fact what we get. So here it is. Sure enough, here's our 1.8 volts that we got. Here it's that reflects, changes sign, comes back, pulls us down, changes, reflects, changes sign, comes back, and so we see the ringing. If you can understand and keep track of all of these reflections back and forth to understand what we see as the net voltage at the far end load, if you can keep track of that, then you really understand the behavior of transmission lines. And this is a great tool just to exercise that understanding. You're not going to design your system using this tool. You're probably not even going to simulate even anything more than this simple problem with this tool. If you have a more complicated problem, you understand what's the received voltage, you're going to use a SPICE circuit simulator to do that. And if you go back to, will be able to exercise your understanding of the behavior of signals on transmission lines with this tool. So be sure to return back to my Substack column for November 17 of 2025 and read some of the background on how to think about signals propagating on transmission lines, and check out some of the other references listed there. Hi, and welcome to this episode of Office Hours with Professor Eric Bogatin. This is for November 17th, 2025, and this is really the third in our three-part series of videos describing some of the really cool online signal integrity analysis tools from Sierra Circuits. In this video, I'm going to review for you the maximum current and trace resistance analyzer. For a lot more of the details about the background of what it is we're trying to calculate here and the application of this information, be sure to check out the details in my Substack. You can get there either by typing in this URL. There's a link in the show notes, and you can use this QR code that will take you to the Substack column, and you can subscribe for free to receive links to all of my future posts as well. Let's get started, and to do that, we're going to go to the Sierra Circuits website. Here is the URL to get there, and then we're going to go to look at the PCB analysis tools. Once we get to the Sierra Circuits website, we want to go over here under Designer Tools. This is all their tools. If we just click on the top banner, that'll bring up the list of all the tools here. And the one that we're going to look at in this particular video is the guy down here, Trace Width, Current Capacity, and Temperature Rise Calculator. So we click on that link and it opens up this particular online tool. You can read some of the details here. Important to note that the analysis, the calculations that are done under the hood are based on the IPC 2152 spec. This is a commonly used spec to help us analyze and estimate the maximum current in a trace. With that, we're going to click on the banner over here that will take us to the tool itself. And here is that tool. This will allow us to analyze first the resistance of a trace, which we should be able to do in our head anyway if we understand the concept of sheet resistance. And so if this concept of sheet resistance is a little foreign or you're a little confused about it, be sure to check the Substack column for this issue of November 17, 2025, and you'll see the links to the chapter in my textbook where I go through the details of how to think about trace resistance, sheet resistance, and also about two-wire and four-wire resistance measurements. You should really only use the calculator for the resistance of a trace after you first estimated what that trace resistance is, and I walk you through how to do that in the Substack column. So we're going to define the geometry of the trace, the length, the width, and the thickness of it, and then we're going to get two pieces of information. The first is the resistance from end to end, and the second is what the maximum current we can put through that trace is before it gets too hot. And what does too hot mean? It's a very vague term. My rough rule of thumb is using a 40-degree rise over ambient. And if it goes up 40 degrees, then it means it's noticeable. Doesn't mean it's going to break, or doesn't mean it's not going to work after that point. It just is kind of a rough measure of the maximum current you can put through a trace before you have to worry about the temperature rise. And of course, if you put too much current through the trace, it heats up more as it dissipates more power. The resistance increases, it heats up even more. The temperature rises even more, and you get into a state called thermal runaway. And I show an example of this in a webinar that I did with my buddies at Telden and LaCroix, and there's a link to that also on the Substack column that you'll want to take a look at. So those are the two things that we're going to calculate in this online tool. Let's first look at trace resistance. So here's how we're going to set up the geometry. So we're going to look at the ambient temperature. It's pretty arbitrary, not really important here. The trace thickness is, in this case, we can select either ounces of copper or mils. We use ounces of copper, and we'll use a 1 ounce of copper typical of surface traces. And of course, we've selected here the external trace microstrip. You can have an internal trace as well. Nice picture to illustrate this. And this is all based on, again, that IPC 2152 spec. It empirically has measured temperature rise in different stack-up configurations. And then in order to look at the maximum current or the resistance, my rule of thumb is using a value of about 40 degrees C as the temperature rise over ambient, and then comes the trace width. And in this case, we're going to use a trace width. Again, this is completely up to you for your geometry. I like using a width of 6 mils as a starting place. If you look at 1 ounce copper that is 6 mils wide, the cross-sectional area of that trace is actually less than a human hair. And so this is kind of a way of calibrating your intuition, your engineering judgment about how much current you can put through a trace. So we use 6 mils wide. Now, before we calculate what the current is, this is going to give us the maximum current carrying capacity based on the IPC 2152 spec. It will also calculate for us what the resistance is for the trace. Before we push that button, we always want to use rule number 9, anticipate before we simulate. So let's see, if it's 1 ounce copper, we know the sheet resistance is 0.5 milliohm per square. And if you're confused what that means, be sure to check out the chapter in my textbook where I go over calculating sheet resistance, an incredibly powerful method to do simple estimates of trace resistance. So it's a half a milliohm per square, 6 mils wide, 1 inch long. The number of squares in that line is 1 inch divided by 0.006. That's about 160 squares. So we have a half a mil per square. We have 160 squares in series. Each one is half an ohm. That means we're talking about half of 100, about 80 milliohms as the resistance we expect to see. And having done this before, I know that I can get at least an amp through a 6 mil wide line. So let's push the calculate button and see what we get. And so based on the IPC 2152 spec, 6 mil wide line, 40-degree temperature rise, that says the maximum current capacity before we have a 40-degree temperature rise is 1.4 amps. Really close to what I would have anticipated. Says you can put an amp through there without even blinking, not worrying at night. Doesn't really tell you what the fusing current is. That is very strongly dependent on the thermal environment. No simple analytical approximations for that. And we estimated about 80 milliohms as the series resistance for that trace. Let's come over here for 1 inch long line, resistance at ambient, 81 milliohms. Really close to what we expected. That's great. One last example we're going to run, and that is 20 mils. So 20 mils, we ought to be able to get about 3 amps of current before we have that temperature rise. So let's try our 20 mil wide line, and now we're going to calculate what the maximum current is. We calculate it, and here it is 2.8, pretty close to 3 amps of maximum current. So that's really the best way of using the tool. Now, you can also say, well, okay, if I want to send 5 amps of current through a trace, and I don't want more than 40-degree temperature rise, what's the IPC 2152 spec say for the conductor width that I need? And this is how the other way of using this tool. We can calculate what the width is for 5 amps of current, and that is 53, roughly 50 mils wide. This is pretty remarkable. That says for 5 amps of current, all it takes is a 50 mil wide trace. And so you want to rethink how you do power distribution. If you're sending 5 amps, even 10 amps, if we look at 10 amps of current and we ask what line width do we need, we're talking about 175, 200 mil wide lines. If we use a 200 mil wide trace to distribute the power for 10 amps, that's all it takes. And so this gives us a little bit of insight, some engineering judgment to rethink how we do power distribution. If you're dealing with multiple amps, 10 amps of current, you want to rethink, do you really need a power plane to distribute that current? You can use a power trace on a signal layer that's 200 mils wide and manage up to 10 amps of current really easily. And I always recommend, if you're doing 3 amps, which is a lot of microcontroller based IoT kind of designs, maximum of 3 amps at any time, even a 20 mil wide line is all it takes to distribute 3 amps of current. And at any point, if you're concerned about this, worried about this, you want to convince yourself, wow, that's the case, you want to use a simple little test board that allows you to send a few amps of current through a test line and measure what the temperature rise is. And I show you an example of doing that in the video that's linked on my Substack site for this edition, November 17, 2025. So this is a really useful tool in order to explore these two questions of what is the maximum current we can send through a line before it gets too hot, and what is the resistance of the line in milliohms given the line width.